Imagine an electrical circuit as a racetrack, a high-speed oval where something is constantly in motion, completing lap after lap. It's a dynamic system, always ready for action. But instead of cars, electrons race around, zipping through the conductive pathways at incredible speeds. These tiny particles are the lifeblood of our electronic world. A circuit is a closed path, a continuous loop that lets electricity flow uninterrupted. It's a carefully designed route, ensuring power gets where it needs to go. If there's a break, even a tiny one, the flow stops immediately, halting the entire operation. Just like a missing bridge on a track prevents cars from completing their journey, a break in a circuit stops the electrons in their tracks. Every device you use, from the simplest to the most complex, from phones, keeping us connected, to lights, illuminating our world, depends on these closed loops to function correctly. Without them, they're just inert objects. The purpose? What's the grand design? To guide electricity safely and efficiently from a power source like a battery or a wall outlet, make it do something useful. Whether it's lighting up a room, playing music, or running complex calculations, then return it safely back to the source, completing the cycle. Think of a circuit as a hose directing water. Without it, the energy, like water, just spills out uselessly, going nowhere. For example, to light a bulb with a battery, a simple yet fundamental application, you need a complete loop. A continuous, unbroken pathway, from one end of the battery, the positive terminal, through the bulb, causing the filament to heat up and emit light, and back to the other end, the negative terminal, completing the circuit. Flicking a light switch, a simple everyday action, completes or breaks this loop, connecting or disconnecting the flow of electricity, letting you control the flow of power with a simple gesture. Every time you use electronics, big or small, you're controlling a circuit, manipulating the flow of electrons, lowering or raising that bridge for electrons, allowing them to continue their journey or stopping them in their tracks. Understanding this closed path, this fundamental concept, is your first step into the fascinating world of electronics. You get to design the racetrack, to create the pathways that power our modern world. Every circuit, no matter how complex, is built from a few key parts. Understanding these fundamental components is the first step to creating your own electronic marvels. First, you need a power source, then conductors, a load, and finally, a switch. The power source, typically a battery in simple circuits, provides the necessary push or voltage for electrons to move and create an electrical current. It's the heart of your circuit, providing the energy for everything else to function. Wires or conductors, often made of copper, act as the roads connecting all the components together, efficiently letting electricity travel from the power source to the load and back. The load is the component that actually does the work. This could be something like a bulb lighting up, converting electrical energy into light, or a motor spinning, transforming electrical energy into mechanical motion. Without a load, the circuit is essentially incomplete and has no practical purpose. The switch is your control element. Flip it on to close the circuit, creating a continuous path and allowing electricity to flow freely, or flip it off to break the path, stopping the flow of electricity. A light switch in your home is a perfect example of this simple control mechanism. It lets you safely and easily control the circuit powering the light without directly touching any wires. In every electronic project, from the simplest to the most complex, these four fundamental parts work together in harmony. Power originates from the source, travels through the connecting wires, and then into the load, before returning to the source. But only if the switch is closed, completing the circuit. That's the basic recipe, the foundation upon which any circuit is built. And with a solid understanding of these components, you can build anything from a simple flashlight illuminating your path, all the way to a complex robot capable of performing incredible tasks. Electricity moves through a circuit thanks to voltage, the push from your power source. A battery's negative terminal has extra electrons, the positive wants them, creating pressure. Close the circuit, and electrons flow from negative to positive, through the wires and the load. This flow is called current. In a bulb, the filament resists the current, heating up and glowing to make light. The electrons lose energy in the load, turning it into light or motion. Afterward, they return to the battery, completing the loop. As long as the circuit is closed and the battery has power, this flow continues. That's how circuits make things happen. When it comes to connecting electrical components, there are generally two primary methods to consider. Understanding these configurations is crucial for anyone working with electronics. The first is a series circuit. The second is a parallel circuit. In a series circuit, all components are connected sequentially, forming a single continuous loop. Think of it as a chain, where each link represents a component. This means electricity has only one path to flow through the entire circuit. The current is the same at every point in the circuit. Consequently, if one part fails or is disconnected, the entire circuit is broken and everything stops working. This is similar to how old-fashioned holiday lights used to work. If one bulb blew, the whole string went dark. Another characteristic of series circuits is that the voltage is divided among the components, so adding more loads like light bulbs results in each bulb receiving less voltage, making them appear dimmer. Now let's consider a parallel circuit. In this configuration, each component is connected along its own independent branch, much like multiple lanes on a highway, allowing traffic to flow independently. Therefore, if one branch experiences a break or failure, the other branches continue to function without interruption. Furthermore, each branch in a parallel circuit receives the full voltage from the source, ensuring that all connected devices operate at their designed power levels. The electrical system in your home is a prime example of parallel circuits in action. You can turn off a lamp in one room, and the television in another room will continue to operate normally. While series circuits are simpler to construct, they are inherently less reliable. Parallel circuits offer greater practicality and resilience for most applications. A solid understanding of the differences between these two circuit types is essential for designing efficient and effective electrical systems. Therefore, carefully consider the specific requirements of your project when deciding which setup is most appropriate. Working with electricity is rewarding, but safety comes first. Never use wall outlets for experiments. Stick to low-voltage batteries. Even with batteries, avoid short circuits. They can overheat wires and cause fires. Always check your connections before powering up. Don't touch circuits with wet hands and work with one hand when testing live circuits. If you feel tingling or see smoke, disconnect power immediately. As circuits get complex, use schematics, universal maps with symbols for each part. Learning these symbols lets you read and share designs worldwide. Schematics make building and troubleshooting much easier. Mastering safety in schematics unlocks endless possibilities in electronics.